Good afternoon, everyone. Today we are hosting our alumni, Michał Pawlak. Michał was doing his PhD under the supervision of Igor Soszyński, working on binary stars and eclipsing binaries. And since then, he's working on binary stars, but in various configurations. After his PhD, Michał spent some time in Prague, in Czech Republic, then in Krakow, and now he's in Lund. He's a researcher in Sweden, and he's gonna tell us about the search for Dormant Black Holes. The floor is yours.
Thank you very much. Thank you for the introduction and the invitation. I'm really happy to be here again and to have an opportunity to speak again in the very same room I defended my PhD a couple of years ago already. And what I'm going to talk about today is exactly the search for dormant black holes. So before we get to the search, let me tell a few words about black holes themselves. Why do we care about them? Why they're interesting? Not sure. Yeah, why this thing does not disappear? Okay. Okay. Height floating. Height floating. Oh, okay. Yeah, sorry. So yeah, let's get back to the black holes and why do we care about them? So first of all, black holes are the end products of the evolution of some of the most massive, most extreme stars that we can observe in the universe. They can be some of the most powerful sources that are observed in the problem. So we still have a problem. Yeah. Is that with the... Oh. Huh. I'm sure. And let's share again. Can we see it now? Okay. So yeah, back to the topic. I hope it will. And now we still again have this thing. So I hope everything is still in place. Great. So black holes are interesting because they are source of the gravitational waves, which is the new field, new very exciting field that's very recently emerged over the last decade and already showed quite a few very interesting results. And there are probably many other reasons. Last but not least, we still don't fully understand the physics of black holes. So quite a lot of motivation to look for them, but there is also one rather significant problem, which is that black holes are quite hard to detect because, for obvious reasons, they are called black holes because they do not emit electromagnetic radiation, and most of our methods using observational astrophysics are focused on electromagnetic observations, with the one notable exception of gravitational waves that I already mentioned. So this means that if we want to detect black holes using electromagnetic observation feeds, photometric, spectroscopic, or astrometric, we usually need to detect them indirectly. And there are various methods to do this. First, probably the oldest one, the original way to detect black holes or black hole binaries was the X-ray observations. So in this case, we have a binary system where we have a black hole and another star, normal star, non-compact star, which is accreting mass onto a black hole. The mass in the accretion disk is heated to extremely high temperature, and it starts to emit very highly energetic X-ray radiation, which is not that common in the universe. It's a very characteristic feature of, for example, binaries with complex companions. So that's a pretty straightforward method to pinpoint this type of objects. Till now, more than 20 X-ray binaries with black holes have been detected, which till quite recently was the most prolific method of black hole discovery. Recently, a few other discovery channels emerged. One of them is the astrometric observations. So again, in the binary systems, but in this case on binaries with much broader objects, we can also detect black holes indirectly based on the astrometric motion of, again, a visible companion orbiting around the black hole. 3 such stars have been detected so far. The latest was published last year by the Gaia Consortium. Probably more will come in the coming years, but so far this has already been quite exciting. The limiting factor here is that for astrometry, we can only detect black holes on quite broad orbits when the astrometric modulation from the visible companion is quite large. So it's, in a way, it's kind of the opposite of the X-ray observations where we detect the closest binaries. Here we look at the binaries at very large object orbits, at orbits of tens to hundreds of days. Another method is gravitational microlensing, which is particularly interesting because, as far as I know, this is the only method that allows us to detect single black holes. So in this case, we don't necessarily need a binary companion. We just need, but we still need another star to pass behind the black hole that acts as a lens and gets magnified. And in a sense, we can detect the object that is invisible, that does not emit the mass itself, but acts as a lens, so magnifies the light of the star that passes behind it. Of course, here the limiting factor is that gravitational lensing is rather rare event, like one of these 1 in a million events. So we really need a large sample of stars to get such events, and it's also like 1 in a time event. So basically, if we miss it, we won't get a second chance to find a black hole this way. But despite this limitation, there has already been a couple of black holes and black hole candidates discovered this way. Here is one example. And finally, we of course have gravitational waves. So very rapidly developing over the last decades. And for the moment, this is actually the channel that led to the discovery of the largest number of the stellar mass black holes. So currently there are over 100 black holes discovered by gravitational wave detectors, LIGO and Virgo. Obviously, there are also new planned missions like LISA. So we expect even more. The point with gravitational waves is that it's only sensitive to the very last point of the evolution of the black hole binary system. So the moment when the two black holes are about to merge and they actually merge. So in that sense, once we detect this black hole binary, it's no longer a black hole after we get the gravitational signal. But the results from the gravitational wave detections are quite promising and quite amazing in a sense, because with hundreds of such detections, we know that there must be really large population of black holes that that has led to the formation of such mergers. So in that sense, we only know a relatively small number of progenitors of black hole mergers. So for example, X-ray binaries, because most of the black holes in binary systems with a stellar companion that we currently know are the ones discovered with X-ray observations. There are about 20 of them, plus a handful of discoveries from astrometry and microlensing. So in total, a small tens of systems. This is likely only the scratching the surface, only the tip of the icebergs. The majority of the population of the black hole binaries probably still remain undetected. How much we really don't know, even though there are theoretical estimates that says that we should have around 1 million of black holes, stellar mass black holes in the galaxy itself. So there is still quite a lot of room for discovery here. The question is if we can still detect these systems that are not close enough to be X-ray binaries. They are not in the range that Gaia astrometry is sensitive to, and we weren't lucky enough to get them to act as a gravitational lens. And the answer is yes, at least in some cases, we can still discover such objects using the phenomenon known as the ellipsoidal variability. So ellipsoidal variability is a type of photometric variability that is observed in binary systems where at least one of the components is tidally deformed. It's deformed by the gravity of the companion, so it's no longer spherically symmetric. It takes this shape, which is commonly referred to as ellipsoid, even though it's technically not ellipsoid in the strictly mathematical sense. It's more like an egg or a teardrop shape. The point is to have this deformation, we just need another massive object in the system. It doesn't have to be visible. So of course, in most cases of ellipsoidals, it's just two regular stars. But we can also observe ellipsoidal modulations in a system where one of the companions is a compact object. So how does it work? Basically, here you can see a projection of how the configuration of the system looks during different orbital phases. And the ellipsoidal variability is a purely geometric effect in a sense that we see a star that is tidally deformed, and we observe it from different angles or from a different sides during different phases of the orbit. So here on this schematic, you can see how the configuration of the system changes and how it is reflected in the synthetic light curve that you can see below. So basically, this light curve has two maxima, which are more or less equal, and they correspond to the point in the orbit where we see the system sort of from the side. So where the surface of the distorted star that we observe is the largest. That's why the maximum of the luminosity. And we also have two minima of slightly different depth. These minima are, of course, in the orbital phase where the size of the cross section of the star that we see is the smallest, and they are of a different depth because on top of the distortion of the star, we also observe a temperature gradient on the surface of the star. So basically, the bottom of the egg is hotter than the tip of the egg. So when the tip of the egg is pointing towards us, the minimum we observe is deeper. And this gives us this relatively characteristic shape, which is like a sine wave, but with two minima that one of them is deeper, another one is shallower. That can be identified in the time series photometry. And in that way, we can identify potential candidates for black hole binaries. And this is how it looks in practice. So these are some of the light curves that has been discovered by OGLE survey. OGLE has been quite successful in detecting such systems. There are currently thousands of ellipsoidal binaries in the bulge and in the Magellanic Clouds. These particular ones come from my one of the papers that was part of my PhD thesis, which was the catalog of the eclipsing and ellipsoidal binaries in the Magellanic Clouds, which actually got updated quite recently. So now we already have a slightly larger sample of ellipsoidal binaries from OGLE, and probably more will come in the future. I'm still waiting for more OGLE discoveries. And yeah, and those stars make a perfect starting point for the search of black hole binaries. The point is to detect which of them are actual black hole binaries, because most of them are probably simple binaries with two regular stellar components. To pinpoint those that actually have a compact companion, we need a bit more data. So we need the information on the masses of the companions in the system. And for this, we need spectroscopy, which is where the foremost come in. So very briefly, foremost is the new instrument that is currently being deployed on the 4-meter Vista telescope in Chile. It's one of the largest multi-fiber spectrographs that currently exist. In total, it's 2,400 fibers that are distributed between 3 instruments, 2 low-resolution spectrographs and one high-resolution spectrograph, 8 fibers each. And it has a particular operation mode, which is different from most of other ESO instruments and telescopes, because the way foremost is going to be operated is not the standard mode that ESO offers, which is like you applied for time and get the telescope for yourself for a couple of nights, as it is with most other telescopes. In case of foremost, the program is slightly different. So there are 26 foremost surveys in total, and all of these surveys are executed in parallel, sharing the focal plane. So basically, there is a large pool of targets that have been provided by all of the foremost surveys, and there is a scheduling mechanism that distributes those targets over the fibers over the whole duration of the foremost project. That the first phase of foremost is 5 years, starting December this year, so in a bit more than half a year. So pretty exciting about it. And for foremost, a few years ago, together with my collaborator Tzvi Maze from University of Tel Aviv, we proposed a community survey to actually observe the ellipsoidal candidates from OGLE, to measure their radial velocities, and based on this to measure the masses of the components of the system and look for those with invisible but massive companions. And this proposal has been accepted. The survey is one of the 26 foremost surveys that will be carried out in the first phase of foremost observations starting this year. And here is a brief overview of the survey. So obviously the main goal is to look for compact objects in close but non-interacting systems. And for this purpose, we're going to observe more than 800 ellipsoidal binaries in the Magellanic Clouds, basically all of the ellipsoidal binaries from the original OGLE 4 catalog from 2016. We are now trying to add those few new ones because there are quite a few new discoveries in the recent catalog that appeared this year. But for now, it's about 800. So basically, all of the catalog ellipsoidal binaries from the previous catalog with periods shorter than 10 days and magnitude above 18 magnitude, which is the limit for foremost. And besides that, we also plan to observe more than 100, so basically all of the known Wolf-Rayet stars in the Magellanic Clouds. And the observation strategy will be to take 6 epochs at random time for each of the targets, and use those epochs to fit the radial velocity curves for the systems and measure the amplitude of the radial velocity. 6 epochs may not sound that much, but the important part here is that we are not going to use these epochs to search for binarity, to search for the periods, to derive the periods, because we already know the orbital periods of these stars. We know them very exactly from our photometry. And assuming that these systems are on circular orbits, which is for most of the closed binaries, this is a reasonable assumption. Assuming circular orbits and the known a priori period, we should be able to fit the RV curves with as little as 6 epochs. And based on the amplitude of the RV curve, we should be able to derive the mass ratio of the system. And having these two information, so first of all, the spectra of the system itself and the information if the system is single-lined or double-lined binary. Of course, if it's double-lined, it means that there is another regular star in the luminous star in the system, so it's not black hole, unless it's a triple, which is also an option. But in most cases, that would just mean that this is a normal double-lined binary, so not that interesting for us. But if it's single-lined and if it has mass ratio that indicates that there is a massive but invisible companion, this companion is most likely a compact object. So here are just a few basic facts about the survey. So here are these 800 targets distributed in the large and small Magellanic Clouds. As you can see, most of them focus on the densiest regions of the clouds, which is good because these regions will be observed most frequently in the foremost surveys. Some of them should get as many as 20 repeated visits. So there is a chance we will actually get more observations than the 6 epochs that we requested. But we'll see about it. We asked for 6, and that's what foremost promised us. So and this should be enough to do our observations. Here is the distribution of the sample on the color magnitude diagram. So again, with blue are the ellipsoidal binaries, red are the Wolf-Rayet targets. Of course, Wolf-Rayets are brighter than most of the main sequence binaries. And here it is, well, we didn't make a specific cut on color here. This is basically achieved by the cutoff period, which automatically removes most of the red giants. Here you can see that the most of these systems are main sequence, and that's for a reason. Because in principle, you could also have black holes in a system where the companion is a red giant. There is no reason why not. The problem is that in such systems, it's much more harder to unambiguously confirm that the companion is a black hole, because if we have a binary where we know that the primary instance of luminosity, so the most luminous companion, is a main sequence star, and we have the high mass ratio, so mass ratio around 1 or even higher than 1. That means that we have a few solar masses companion there, and we would see it in a spectrum. If it was a luminous star, if we don't see it, that means that it's most likely a compact object. For binaries with red giants primary, it is much easier to sort of hide massive, but relatively massive, but still luminous star. So another main sequence star in a system with a red giant primary. So it's just a technical difficulty to unambiguously discover those systems. That's why we decided to focus on the main sequence stars, at least in this program. And here is just some preliminary prediction on what the distribution of the mass ratio we expect, or to be specific, the distribution of the minimum mass ratio, specifically the modified minimum mass ratio, which is a quantity that was introduced by Gomel et al. And this is like the absolute lower estimate on the mass ratio of the system based on the photometric amplitude, or the amplitude of the photometric variability, of the ellipsoidal variability. And it comes from the fact that Gomel showed that the amplitude of the system can be expressed as the function of the fill-out factor, the mass ratio, and the inclination of the system. The rest are basically the constants. Here is the Eddington potential, which is only a function of Q. And this is like C is empirically derived factor, which is also a function of F and Q. So for the systems where we know the amplitude from the photometry, we can get the lower estimate of the mass ratio by assuming the extreme values of the two other variables that goes into the equation. So basically, assuming the maximum possible fill-out factor, so close to 1, and the edge-on inclination, which would both lead to the highest possible amplitude. If we assume these two maximum values and put this in the equation, we then can solve the equation for Q, and this Q will be the absolute estimate, absolute lowest estimate of the mass ratio of the system. And this is a distribution of the mass ratios, the modified minimum mass ratios computed for each of the 800 systems in our sample. And as you can see, there are more than 90 systems with modified minimum mass ratio lower than 1. And the important thing here is that the mass ratio here is computed in the way that we take the ratio where the primary is the more luminous one. So it can be larger than 1, because sometimes mass ratio is defined from 0 to 1. Here it can be larger than 1 because we always take the less luminous to the more luminous component in the system. So basically, if we have a star where the less luminous component is more massive and the primary is main sequence star, that's basically a very, very strong indicator that the secondary might be a main sequence star. Of course, there might be a bit of contamination here caused by the misclassification of between eclipsing and ellipsoidal binaries. So sometimes it's hard to distinguish whether we actually see an eclipse or not in the system. So sometimes the the amplitude of the variability might be too high because, or basically it might be an eclipsing binary. So obviously not an ellipsoidal with a compact companion, because that's an eclipsing binary. But even taking this into account, we still see that there is quite a lot of systems with a potential to be binaries with a compact companion. Also important to note is that while the fact that the minimum mass ratio is larger than 1 is like a strong indicator that it might be a compact binary with a compact companion, the fact that it's lower than 1 does not automatically disqualify a star, because we can, for example, have a star with 10 solar masses primary and 5 solar mass black hole, and it will still work. So in principle, all of these stars are candidates for black hole companions, but those with high minimum mass ratio are the most promising companions, candidates in that sense. And here a quick theoretical estimate of what do we expect to come out from this search. So in 2020, there was a population synthesis work done with MESA by Langer et al., who basically synthesized the population of massive binaries in the LMC. And what they come out, what the result they come up to is that there should be about 60 binaries with a black hole and OB type star companion. So which are exactly the systems that we are looking at here. Of course, this is the total number of all the possible systems in all possible configurations. Not all of them will be ellipsoidal binaries, not all of them will be observable by this strategy. This is another part of work I'm working on right now to kind of do a similar population synthesis, but also taking into account the observable constraints. So like the distribution of the inclinations, the distribution of the periods of these systems, basically to try to predict how many of such systems are observable. And the order of magnitude kind of matches Langer's estimates. It's even slightly larger, but of course there are constraints on the observables. So the ones that we will observe are probably way less than 60. Perhaps a few, maybe tens, but still, in a way, if we find one, it will already be an impressive result, because for now, the number of such systems is basically 0. So, yep, and that's what we're looking at in the formal survey for the Large Magellanic Cloud. But of course, it's not the only project looking for dormant black holes, dormant ellipsoidals. So just quickly here to mention the Gaia project, which I'm also involved in. Gaia so far has discovered more than 6,000 candidates for black hole companions, and more are coming. Of course, there are other surveys, other photometric surveys that are looking for different types of variables, including ellipsoidal variables, current and future. Of course, we are waiting for LSST to come. And as I already mentioned, I hope more binaries from OGLE itself will come. So eventually, we will probably need even a larger survey to follow up all of them, because foremost, the few hundred star surveys that I talked about was basically the limit of the foremost. So to do a survey on the scale of tens of thousands of stars, and we still need a bigger instrument. So this is where the WST comes in. WST is the next generation of the multi-fiber instruments, which is planned to be installed on a 10-meter class telescope. It's currently proposed as the next ESO project after RealT. So the timescale for it is probably around 2040. So still quite a lot of time to wait, but it's already the time to propose the science cases for WST. And I propose one such case, again, to look for whole sky, to perform as whole sky scarage for Dormant black holes in ellipsoidal binaries, basically from all the current and future photometric surveys. So probably instead of hundreds, it would be tens of thousands. That would give us a much bigger overview. So again, if anybody is interested in WST, I encourage you to have a look. Right now, this year, the first concept study of WST has been proved. So another exciting thing to look forward to. So to summarize, foremost is going on Sky this year, and the results we expect from the survey is to discover a few, probably, hopefully tens of compact objects. So the binaries with black hole and neutron stars in the Magellanic Clouds. This will allow us to compare them to the theoretical predictions, to give us the full overview on the population of black holes together with different discovery channels, because the channel I've been talking about is largely complementary to the one that's are already explored. So both X-ray binary, astrometry, microlensing, and gravitational waves. So all of this put together should give us the big picture that hopefully will let us better understand the black holes, their population, their distribution of their parameters, their formation and evolution, and basically the physics behind it. Thank you very much.
We have any questions or comments?
My first question is, did you make any other selection cuts other than the period and brightness?
Other cuts than period and brightness. So in the first step, not. I think in the last step, we also rejected the extremely red stars, because we originally started with a shorter period cut that kind of excluded red giants automatically. So I think we started with 2.5 days, then we moved it to and this would automatically remove red giants itself. Then we extended it to the longer periods, up to 10 days. So this is already where we could potentially get red giant binaries. So here we had to manually remove those few that kind of fall into this, but the principal two cuts were the period and the magnitude.
Okay, so the reason I'm asking is that like a few years back, my student and I did a similar exercise, and we found that if you take multi-wavelength data, for example, multiple photometry, all the way from UV to infrared, then you can try to model CEs, electromagnetic distributions, and try to eject objects that seem to eject objects that don't like a single star. So because at least from my experience is that we get a lot of contamination from contact binary stars. Yeah, so there will be a lot of contamination. So it's important to remove as many contaminants.
Yeah, that's for sure true, and I expect that most of this will be normal binary stars, like with two visible stars. So that's kind of expected. The question is, like, do you think that you can reliably remove for example, distinguish between W mass stars based on the SED itself. Like, can you reliably reject?
At least you can make it very obvious.
Yeah, I remember this work because I remember looking into it. It was done for the bulge or also for
It was done.
both the Magellanic Clouds. Okay, so maybe I need to have a look once more.
Do you use any information in the astrometry already, which is given by Gaia? Is there anything already in Gaia VRF you use to constrain or something?
Not really, because this is Magellanic Clouds. So, I mean, there is astrometry for Magellanic Clouds, but I don't think it's that.
What sizes of orbits you expect? You're right.
Few days. So if you want me to convert it to AU or
Yeah, but you have this radial-velocity measurements in Gaia VRF.
no, there's too faint. No, like the limit is like 14 magnitude,
14 hours.
and here's if you see the yeah, it's basically where it ends. So so I don't think either the Gaia RV or the Gaia photometry astrometry can be of much help for the Magellanic Clouds, at least at the moment.
See, Tomasz, do you have any question on Zoom?
Can you hear me?
Just a moment. Okay, try again.
Can you hear me? No. Okay, never mind then.
We can hear you now.
Oh, so through most of the talk, actually, I thought that you were talking about massive stars. And for those, I would think that if you can get the distortion of the shape to get elliptical light curves, you would also get some interaction with the wind. So if you have a star hotter than B3, you essentially get radiation-driven winds, and there would be some interaction with the potential black hole. So now I would like to ask you, what do you expect is the fraction of the actually massive binaries in the sample that you decided on?
Well, it of course depends what's your definition of massive, but I would expect most of them. So most of them are OB type stars, basically. So massive stars in principle. Maybe early A, but most of them should be B type stars, at least. So yes, there will be. For sure, there will be winds in some of these systems. Again, not sure if I mean, and for sure, some of them will be close enough to have interaction. But this is.
But then it wouldn't be a dormant black hole, right? There would be already some detections of higher energies close to the black hole. Don't you expect that?
It depends. There was one such system discovered a few years ago. The work was, I think, Chenar et al. 2020, when it was a star on a 10-day orbit with ellipsoidal modulation and very faint X-ray signals. So yeah, that's also possible. We're also thinking about looking into X-rays for specific objects where we see the mass ratio that can suggest that there is a compact object in the system, to also apply, for example, for more detailed X-ray observations. Because a lot of LMC was observed in X-rays, but not all, and again, not even if there were observations done, they are often like on the limit of the detection reliability of the of Eurozeta or Chandra. We actually looked into some of the systems. So yeah, that's another thing to look into.
Thank you.
Yeah.
I have a question. Why in your sample you chose only the stars in Magellanic Clouds and you didn't include any from the disk of our galaxy or towards the galaxy board?
That's a question to the ESO-TAC, because I originally wanted to include all of them, but so both the bulge and the Magellanic Clouds, they unfortunately ESO told that this is with the foremost operation mode, it won't be possible to get enough repeated observations in the bulge. It will only be possible in the Magellanic Clouds. So I wanted to do this, but unfortunately.
And galactic disk, maybe?
I don't think there were that many in the disk at the time when we were submitting the proposal. We included all the ellipsoidals, all the main sequence ellipsoidals in the bulge, which was more like 20,000, if I remember correctly. But unfortunately, we didn't get this part of the project. We only get the one that covers the Magellanic Clouds for technical reasons.
I have a question about why to exclude red giants and to include Wolf-Rayet stars. Wolf-Rayets are really difficult to find anything.
Okay, so yeah, I guess I already told why we exclude red giants and why Wolf-Rayets. So Wolf-Rayets were originally not in this catalog. So the original application was pretty different from what it ended up. This is sort of a dynamical process of how this survey was formed. So this is a result of a merger with a different survey led by my other colleague from Tel Aviv, Photometric, who was interested in this particular stars. So this part was added later on with slightly different observing strategy, actually. So for these stars, there are way few of them than the ellipsoidal ones, so we can take more epochs for them. We also will spread those epochs more in time. So and of course here we also are interested in the black holes because there are theoretical predictions saying that up to 10 or even 20% of Wolf-Rayet stars can have a black hole companion. But it also aims at like other type of characterization of Wolf-Rayet stars, which is led by Tomev. But it was added like at a later stage. It wasn't the part of the core project originally. And here it's not only about black holes, it's in general the binarity fraction in Wolf-Rayet stars in general characterization of Wolf-Rayet stars as well.
But the red giants would feel the companion strongly.
No. In this sense, we don't look at the ellipsoidal. We don't expect Wolf-Rayets to be ellipsoidal formed. It's just looking at the binarity and the
giant is quite big, and it feels that something near.
Yeah, but the problem is that you can easily hide a normal star that has a mass of a black hole, but it's a star near.
Okay, so if there's anything that you would not be in between black hole and normal stars.
So yeah, but basically the point was like, if for main sequence stars, if you have something that is free solar masses and you don't see it, you're almost sure it's a black hole. If you have a red giant and you can still have like free solar mass star kind of hidden in the spectrum because of the luminosity of the red giant.
Yeah, but some expect that when we have this multi-wavelength observation, we see that maybe something is hotter there. and it will be, let's say, Fox companion.
That might be the case. I remember also doing some work with SED fittings, so it can often tell you quite a lot, but it also relies quite strongly on usually on how well you can constrain the blue end of the SED, which sometimes can lead to quite a strong uncertainty. So I think it's definitely worth looking into, but have to check how reliably we can include or exclude objects based on this in this search.
So another option is just also to do disentangling, as Shenar showed, right? That was mostly about the evolved stars. And it's crucial to do the spectral disentangling to actually see if there is really no components visible. That was one of the idea, but I guess the foremost data wouldn't be enough because it's 6 epochs data. So yeah, I don't know, maybe just follow up with some of those candidates.
That's an option. We plan to do. There is a software done by the Tel Aviv group, which is named .core, which kind of does this thing like spectral disentangling into like multi-template fitting to see if the spectrum can be fitted better with a single object or two object spectrum. And we'll certainly plan to do it. How well this can be done based on the formal spectra itself, we'll see in practice. But once you identify a handful of good candidates out of 800, it's much easier to get, for example, high-res observations for the stars. For many of them, we probably will also get high-res observations from another survey that is that will be done in the Magellanic Clouds that's led by Maria Rosaccioni from Potsdam. This is 1001 Magellanic Cloud fields, so they also plan some high-res observations from Formos as well, so there might be more than counts.
See any more questions? So fingers crossed for Formos. Thank you, Michał. Thanks a lot. Next week, we'll have a visitor from Prague, Andrzej Pecha, will tell us about the multi-dimensional simulations of binary systems. See you there. Thank you.
It was lovely. Thank you.